CERN has uncovered matter behaving in ways it shouldn't. Particles nobody expected to find, and signs that some of physics' most trusted theories might be missing something. These are CERN discoveries that terrified the scientists who found them. Alright, news of this just came out last month. Scientists at the Large Hadron Collider have just detected something that could officially break our current understanding of physics. Quite the statement, so let's dive in. So they've been digging into some incredibly rare subatomic transformations called electro-weak penguin decays. It sounds funny, but it's a real term. As the researchers stated, quote, "The term penguin refers to a specific type of decay of short-lived particles. In this case, we study how the B meson decays into 4 other subatomic particles, a kaon, a pion, and 2 muons. With some imagination, one can visualize the arrangement of the particles involved as looking like a penguin." End quote. This specific transformation is ridiculously rare in nature. The researchers explain that, quote, "For every million B mesons, only 1 will decay in this manner. Because it's so rare, it's the perfect place to look for anomalies. If there are weird, undiscovered heavy particles floating around the universe that we can't see, they'd alter the math of this decay process." That is exactly what happened. The team tracked approximately 650 billion B meson decays, isolated the penguin events, and hit a major wall. The physics didn't add up. Basically, the particles are flying off at angles and energy levels they shouldn't be capable of. There's a tiny chance this is a statistical fluke, but it's also very likely we're looking at brand new physics. According to this news story, I'm not a scientist, in case you haven't already guessed that. For decades, physicists were missing something. They had this big theory that explained how particles work, how they interact, why they behave the way they do, but there was a hole in it. One particle that the whole thing predicted should exist, but nobody had ever actually found. They called it the Higgs boson, and in 2012, CERN finally found it. Years of work, billions of dollars, and the thing was real, exactly where they thought it would be. Big moment, but then people did the math on it. Specifically, they took the mass they measured and ran it through equations that described the energy state of empty space, and the results were a little alarming. The way it's been described is this. Imagine a ball sitting in a small dip on a hillside. It's not rolling anywhere, so it seems stable. But it's not at the bottom of the hill. There's a lower point further down. Our universe might be like that ball, sitting still, looking fine, but not actually in the most stable state it could be in. If that's true, then at some random point, a tiny patch of space could flip into that lower state, and that patch would expand outward at close to the speed of light. The physics inside it would be completely different from the physics we know. Anything it passed through just wouldn't exist anymore in a recognizable way. Now, the math also says this would take longer than the current age of the universe to happen. So, not really something we need to worry about, thankfully, but the unsettling part is that just before they found the Higgs, this was just hypothetical. Protons and neutrons aren't actually solid little balls. They're made of even smaller things called quarks, which are normally stuck together and can't be separated under ordinary conditions. But if you get things hot enough, those quarks become loose. You end up with this hot soup of free quarks all swirling around together. They say that's what existed in the very first moments after the Big Bang, and CERN's ALICE experiment has been recreating it by smashing heavy atoms together at incredible speeds. Before they actually did this, most people assumed the soup would behave like a gas, with particles bouncing around loosely, not really connected to each other. Totally reasonable assumption, but it was wrong. The soup moved like a liquid, almost no resistance, incredibly smooth flow, better than water, actually. Almost no friction at all. For something made of the most fundamental building blocks of matter running at insane temperatures, that was genuinely shocking. And what it means is that the very early universe was more like a fast-moving, incredibly smooth liquid. That may be a hard image to get your head around, because it certainly is is for me. Since the 60s, the understanding was pretty simple. Quarks come in two types. You can have three stuck together, that's what protons and neutrons are, or you can have two paired up, which makes a different kind of particle. Those were the options. People had speculated that other combinations might exist, but after 50 years, nobody had ever seen one. Then an experiment at CERN called LHCB was watching a heavy particle break apart, tracking where all the pieces went, and they kept seeing a pattern that didn't fit. The signal was clear enough that they couldn't explain it away. After a lot of checking and rechecking, the conclusion was that they were looking at a particle made of 5 quarks. That might not sound all that dramatic to us, but for the researchers, this was a very big revelation. They'd never seen this before. And then the question became, were these 5 quarks all tightly fused? Or was it more like 2 separate particles that had just happened to be clinging to each other? That argument is still going. Once the first Penta Quark showed up, you'd think the shock would wear off, but it didn't. CERN kept collecting data, and the data kept throwing out new combinations. In 2022 alone, LHCB announced a whole set of new exotic particles. 4 quark versions, more 5 quark versions, again, configurations nobody had seen before. They went through enormous amounts of data, checked everything multiple ways, and the particles kept showing up. Now, the force that holds atomic nuclei together was supposed to be one of the better understood things in physics, but every new exotic particle that shows up kinda shows that it's more complicated than scientists thought. Quarks can apparently arrange themselves into all sorts of combinations that nobody thought was possible before. When the universe began, it should have made equal amounts of matter and antimatter. Matter and antimatter destroy each other on contact. They just annihilate into energy. So if everything started out equal, it all should have wiped itself out. Nothing would exist. Obviously, that didn't happen, or you wouldn't be watching this video. I wouldn't be here making it. Matter won by a little bit, and that little bit is everything that exists. Nobody really knows why. CERN has been trying to find out by looking for tiny differences in how particles behave compared to their antimatter versions, and they found differences. The problem is those differences are way too small. They don't come close to explaining the scale of the imbalance we actually see in the universe. Other experiments at CERN have tested whether antimatter at least responds to gravity differently. Maybe that was the missing piece. Apparently not. It falls exactly the same way normal matter does. So we know matter and antimatter behave slightly differently in certain ways, we just can't figure out how those differences add up to a universe full of matter and basically no antimatter. Almost everything the LHC creates falls apart almost instantly, but some theories predict particles that could survive much longer, long enough to actually travel through the detector or even get stuck inside it and break down well after the collision. Seconds later, maybe minutes. CERN's built specific searches for these, looking for particle activity that shows up in the wrong place, so things that appear out of nowhere inside the detector with no obvious cause. So far, nothing's been confirmed. The standard way of analyzing collisions is built around the assumption that everything decays almost immediately, right at the collision point. If particles exist that don't do that, that wander through the detector or linger inside it, the normal methods they use to analyze this stuff just wouldn't work. They just missed them. There is a proposed detector called Methuselah that would sit on the surface above CERN, specifically designed to catch these kinds of particles if they exist. And sure, nothing I'm talking about here has actually been discovered, but the fact that something like that is being proposed at all is pretty cool. In 2011, a group of physicists thought they might have broken one of the most fundamental rules in physics, that nothing can travel faster than light. They were firing a type of particle called a neutrino from CERN in Switzerland straight through the Earth to a detector in Italy. Neutrinos can pass through solid rock, so the journey isn't a problem for them. The team was just measuring how long the trip took. When they looked at the results, the neutrinos were arriving early, Not by much, about 60 billionths of a second, but if that was real, those particles were moving faster than light. And if that was real, a huge chunk of physics was wrong. They published their findings and asked other researchers to help them figure out what was going on, because this was a huge deal. For months, nobody could find the problem. But eventually, someone found it. Okay, this is a bit anticlimactic, but a cable in the timing equipment wasn't fully connected. That tiny loose connection was throwing the timing off just enough to make the neutrinos look faster than they were. Once it was fixed, the results came back normal, but hey, for a short while, this was incredibly exciting. LHCB has been watching how certain heavy particles break down, looking very closely at what comes out. The theory predicts that two specific types of lighter particles, electrons and their heavier relatives, muons, should appear at roughly the same rate in these decays. But the data kept looking slightly off. Muons were showing up less often than they should, not by a lot, but consistently across multiple different experiments over years. Physicists started drawing up models for what kind of undiscovered particles could be causing it. Then more data came in, and by 2023 the numbers had drifted back towards what the theory predicted. The anomaly seemed to have faded. It might have been nothing, but that's gotta be confusing and frustrating. You watch a pattern in the data for years, you write papers about it, try to figure out what it means, and then you find out it could just be faulty data. The LHC doesn't just smash individual particles together. In some runs, it smashes large atomic nuclei into each other. The energy packed into collisions like that is so extreme that the temperature briefly reaches something in the range of trillions of degrees. The core of the sun is around 15 million degrees, so these collisions are many times hotter than that. At those temperatures, the matter we know basically stops existing in the form we know it. The particles that make up atoms come apart, and you get this hot soup of the most basic stuff there is. As I mentioned at the top of this video, that's the same state the universe was in during its very first moments after the Big Bang. A machine built by people sitting underground in Switzerland, of all places, is briefly creating conditions that haven't existed since the universe was a fraction of a second old. That is just insane. Mind blown. All right, guys, that has been our list for today. Thanks so much for checking it out. I've been your host today, Olivia Kozolowski, and I will see you again soon. Goodbye.